Hi guys, you might have heard that some algorithms such as binary search need the data to be ordered. So today we're going to go over some ways that we can tackle this problem. So what is data sorting? It's simply the arranging of data into a meaningful order, such as ascending or descending for numbers or into alphabetical order for letters. For humans, this task is fairly easy. We can look at a series of values and almost instantly recognise if the order is wrong and move the relevant information around until it's in the correct order. But unfortunately for us, computers don't think in the same way that we do, so we have to use a computer algorithm to solve this problem. In this video, we'll be covering a couple of different approaches to the problem. By no means is this a comprehensive guide to all sorting algorithms, as there are absolutely loads of them with various uses, but we'll cover some of the core ideas behind sorting and some common algorithms that you might come across. Sorting data has many benefits. It makes it possible for efficient searching of data, such as the binary search we talked about previously, but it can also make it easier for humans to analyse and visualise data. The first algorithm we'll be discussing today is bubble sort. It's relatively easy to understand and makes for a great introduction to sorting data. For this example, we'll be sorting data into ascending order, but with some very minor changes. You can also use the algorithm for descending. Bubble sort works by comparing pairs of values in a list, which in our case I've called num. If the first value is greater than the second in the pair, we'll swap them. So we form a bubble around the first two elements, check if in this case 2 is greater than 1, which obviously it is, and then we swap those values in the array. We then move on to the next pair of elements and compare them. In this case, 2 is not greater than 6, so the elements stay where they are. This process continues through until we've checked all of the pairs in the array. So here you'll see the final comparison. We'll check that 6 is greater than 3, which it is, so we will swap those two values around in the array. Now you're probably looking at this data and thinking, well, hold on a minute, these numbers aren't in order. And that's because we've actually only done one iteration so far of the bubble sort. So we begin the whole process again, starting with the first pair of elements in the array and working down to the last element just as before. So for this last one, 4 isn't greater than 6, so there's no swap, and at this point we've completed this iteration of the bubble sort. Just a quick heads up, you might hear people refer to these iterations as a pass. So now that we've done these two iterations, you've probably noticed that the data is now in order. But the difficulty is, how does the computer actually know this? When the algorithm has iterated over all pairs in the array and no swaps have occurred, we know that the sort is complete. To do this, we can make use of a Boolean flag. In this case, let's call it swapped. We set it to false at the beginning of an iteration and only set it to true if data gets moved around in the array. Now we've got to a point where we have to switch around values because 4 is greater than 3, and at this point we set the swapped flag to true, and the algorithm now knows that it needs to do another full iteration of the bubble sort. So we can see here that no swaps have occurred during this iteration, and so we can safely assume that the sort is completed successfully. And that's it. The data is sorted, the algorithm stops running. I mean, if we wanted to do things in descending order instead, we could simply change the check when we compare pairs to see if the first value in the pair is less than the second, and simply by doing this, we'll get our numbers in descending order. Now, I'm sure you'd agree that that's a lot of steps to go through just to get your data in order. As the data set gets bigger, the process takes exponentially longer. The best case for a bubble sort is that the data is already in order, so we just need to do one iteration where no swaps occur and we're done. This gives us a time complexity, in best case, of ON. On the other hand, if let's say the data is in descending order and we're trying to sort it by ascending, then the time complexity will be ON squared, which certainly isn't ideal because we have to make all the possible swaps to all the numbers to get it in the correct order. Now the main benefit of bubble sort is that it's relatively easy to implement and understand. Elements are swapped directly in the array, so there's very little memory overhead, and it can be a quick way to just check if your list is in order. So for the remainder of the video, we're going to move on to a slightly more efficient algorithm. Merge sort is a recursive sorting algorithm that will consistently sort large datasets much faster than bubble sort at the expense of requiring extra memory. It's part of a family of algorithms we call divide and conquer. This means that we divide the data set up into sublists that we can solve for more easily. Let's get into the merge sort. Just a quick heads up, I'm not going to be covering any of the specifics of implementation in this video, but instead we'll focus on the core concepts behind merge sort. If you'd like to have a go at implementing this algorithm yourself, I'll include some resources to help you along in the description. We start out with our unsorted array, which as you can see here contains 6 values, 2, 1, 6, 4, 3 and 5. We begin by splitting the data in the middle to give us 2 subarrays. We continue this process until the array has been broken down into individual elements. At this point in the merge sort, the elements are the only things in their respective lists, and so they must be sorted. All we have to do now is start merging them back together. Once we have the items in individual lists, we can then begin to sort and merge them. We compare values and put them back into arrays in order, and we continue this process until we're left with an ordered list. For example, if you look at the leftmost half of the array on the second row, there are 2 lists, the first containing the numbers 1 and 2, and the second containing 6. So the comparisons might go a bit like this. You compare 1 to 6, and the 1 in this case is smaller than 6, so that goes first in the next array. And then you might compare the 2 with the 6, which once again is smaller than the 6, so that goes in second, and then finally we merge the 6 in. This process is done for both halves of the data set, so at this stage you can see we're left with 2 lists, one containing 1, 2 and 6, and the other containing 3, 4 and 5. All that's left to be done now is make comparisons between the 2 lists that we have, and once that's done we'll be left with our final ordered array. So as you can imagine, when comparing to something like a bubble sort, a merge sort is significantly faster on large amounts of data. The main benefit of a merge sort is its consistent speed on any size of data. The algorithm is always splitting the array in 2 and results in a time complexity of O(n) log n in all cases. Merge sort isn't without its disadvantages. Due to the need for temporary arrays to hold the split data, it requires extra memory equal or larger to the size of the initial list, so it might not be ideal for sorting large amounts of data. Thanks for tuning in everyone. I hope the video has been useful, and as I've mentioned, if you'd like to know a little bit more about the topics I've discussed today, please feel free to have a look at the information I've provided in the description.